The crystal-clear waters of Lake Tahoe might seem an unlikely place for a major earthquake, but a closer look at the geology tells a different story. Have you ever wondered what lies beneath the sapphire blue of Tahoe's depths, and whether that hidden world could shake the basin one day? As a new generation of scientists warns, the western shore of the lake hides a significant normal fault system, the West Tahoe Dollar Point fault zone that could someday rupture in a multi-meter slip event, potentially unleashing magnitude 7+ shaking and tsunami-like waves across the lake. In fact, researchers calculate that a full rupture of this fault, roughly 50 kilometers, about 31 miles long, could reach about magnitude 7.2 or 7.3. That is not a forecast of an imminent quake, but rather a plausible scenario based on geological evidence. Nevertheless, the what-if is eye-opening. An earthquake that large could lift or drop the lake floor by several meters, sending long-period oscillations called seiches and a tsunami across Tahoe's shores. Why has this risk not been front-page news? Lake Tahoe sits at a junction between tectonic realms. To the west lies the Sierra Nevada microplate, moving roughly northwest at about 6 millimeters per year relative to North America. And to the east, the Basin and Range province, characterized by crustal stretching. Tahoe is in a transtensional zone. Some of the Pacific North America plate motion is taken up by east-west extension on north-south faults, and some by northwest-southeast shear on other fault sets. The result is that many Tahoe faults are north-south trending normal faults, meaning one side drops down relative to the other as the crust pulls apart. Not surprisingly, geologists describe the Tahoe Basin as a classic intermontane normal fault domain, bounded by other normal fault domains to the north and south. These north-south faults accommodate most of the east-west extension in the region. Importantly, although these faults carry huge geologic forces, they have been quiet on human timescales. Only small tremors are recorded instrumentally. However, the geologic record, scars in the earth, offset sediments and underwater slides, shows they have broken in much bigger quakes on timescales of thousands of years. One of the major players is the West Tahoe Dollar Point fault. This normal fault zone defines the west side of the Tahoe Basin. Onshore, it forms steep, cliff-like scarps along the west shore. The bedrock on the eastern side of Lake Tahoe is uplifted relative to the lake basin, which has subsided on the west side. Underwater bathymetry and LiDAR mapping have traced the fault from Emerald Bay, the southwest corner of Tahoe, north past Fallen Leaf Lake, and into McKinney Bay, just south of Tahoe City. It essentially underlies the lake's western shoreline from Baldwin Beach up toward Dollar Point. The 2013 Geosphere study by Jill Maloney and colleagues dubbed it the most hazardous fault in the basin. Indeed, researchers have used high-resolution chirp sonar and cores in Fallen Leaf and Cascade Lake to image the fault's traces beneath the water. These images show the lake floor cut by steep scarps. Each side of the fault faces drop-offs of many meters. For example, Maloney's team saw strands of the fault offsetting Cascade Lake's floor by as much as 7.5 meters, nearly 25 feet. In Fallen Leaf Lake, they found 3 fault traces, one of which showed about 3.7 meters, roughly 12 feet, of vertical displacement during the most recent earthquake on that segment. In short, this fault is far from inactive. It has physically shifted the basin by multi-meter amounts in the mid-Holocene. Seismic reflection and sediment data confirm those shifts. In one investigation, piston cores and chirp profiles in Fallen Leaf Lake recorded a paleoseismic horizon dated at roughly 4.1 to 4.5 thousand years ago. Below that horizon, layers were clearly offset. Above it, they were not, indicating a major event at that time with roughly 3 to 4 meters of slip on the fault underneath. In Tahoe itself, near Rubicon Point, the same disturbance left about 2 meters of apparent offset, dated broadly to the same few thousand-year window. Taking into account older geology, offset of glacial deposits by the West Tahoe Fault implies a long-term slip rate on the order of 4 to 8/10 of a millimetre per year. That is slow, but comparable to nearby active basin and range faults, for example, the Genoa Fault, which produced historical magnitude 7 earthquakes. Researchers conclude that the slip rate and earthquake potential along the West Tahoe Dollar Point Fault is comparable to the nearby Genoa Fault, making it the most active and potentially hazardous fault in the Lake Tahoe basin. The bathymetric surveys and remotely operated vehicle dives have also highlighted just how fresh Tahoe's fault scarps can be. In the famous Emerald Bay area, a 2019 Geosphere report by Craig Schweikert and colleagues found extremely sharp, steep scarps cutting across submerged glacial moraines. These underwater cliffs, sloping 30 to 60 degrees, are unlikely to be very old. On land, such steep fault faces would erode quickly, but underwater they remain intact. Geologists estimate those scarps are younger than about 20,000 years, younger than the last glacial deposits they cut. In other words, the West Tahoe Fault has clearly moved during the late Pleistocene or Holocene. Remarkably, this study noted that over the past about 20,000 years, the West Tahoe Fault and the neighbouring Tahoe Sierra Frontal Fault has slipped almost purely vertically, with no obvious sideways motion. This was a bit surprising given that measurements show the Sierra Nevada moving northwest, but it means these faults are essentially extensional mode today, doing their own thing relative to the plate motion. It also supports the notion that these faults have long records of normal fault earthquakes, even if none have shaken Tahoe in modern history. If we accept that the West Tahoe Fault has produced large earthquakes every few thousand years, we can estimate their size. In seismology, rupture, length and slip give you magnitude. The West Tahoe Dollar Point zone is over 50 kilometres long, with multiple segments. Modelling studies have put numbers on it. For example, Ichino's Jean and colleagues ran a hypothetical scenario, a 48-kilometre by 17-kilometre patch of fault slips with an average of about 2.8 metres, about 9 feet. This gave a seismic moment on the order of 7 times 10 to the 26 dyne centimetre, equivalent to roughly magnitude 7.2. In that model, they assumed up to 4 metres at the centre of slip, tapering off to 0 at the ends, which is a reasonably upper-end assumption. Scientists likewise warned in a public lecture that each of Tahoe's 3 big faults, West Tahoe, State Line North Tahoe and Incline Village, is capable of large ruptures with a maximum magnitude of about 7.3. Note that 7.3 in this context is essentially an envelope of worst-case scenarios, not a precise forecast. It means that if the entire mapped length of the fault broke in one event, the shaking could reach the low 7s on the moment magnitude scale. Other estimates have been a bit lower. A Nevada hazard map scenario listed the West Tahoe Fault specifically at about magnitude 7.1. The key point is that geologic and modelling data converge on magnitude 7 range for a full West Tahoe rupture, certainly in the same league as some of California's biggest earthquakes. What would a roughly 7.1 to 7.3 quake do to Lake Tahoe? Because much of the West Tahoe Fault runs under the lake bed, a large rupture could displace the lake floor. This would generate both a near-field tsunami and a long-lasting seiche. A lake seiche is essentially a giant standing wave or slosh. Numerical simulations by Ichino's and colleagues looked at 3 different fault scenarios in Tahoe, Incline Village, West Tahoe, and the Genoa Fault to the east. They found that the underlake ruptures generate an initial tsunami followed by a seiche that can persist for hours, with peak waves as large as 3 to 10 metres. In that scenario, the pattern of maximum waves showed some locations reaching the higher end of that range. 10 meters is on the order of about 33 feet. That is a dramatic swell for Lake Tahoe. Imagine walls of water tens of feet high, lapping at the Sierra shoreline. This is not just theory. The same LIDAR and chirp studies that revealed faults and offsets have also found evidence of past large waves. Cores in Lake Tahoe and nearby Fallen Leaf and Cascade Lakes contain turbidite layers and landslide deposits that correlate across basins, suggesting they were triggered by strong shaking. In fact, one team noted that slides in Fallen Leaf Lake, Cascade Lake and Tahoe all line up in time, consistent with one or more big earthquakes on the West Tahoe system. Such quakes would almost surely have stirred the lake. In a public write-up, scientist Jill Maloney said the West Tahoe fault is capable of producing a magnitude 7.3 earthquake and tsunami waves up to about 30 feet 10 meters high in the clear blue lake, where expensive homes line the shore. She also noted that these events happen every 3,000 to 4,000 years or so, with the last one about 4,500 years ago, meaning the fault may be overdue for the next one, though overdue in geological terms still leaves wide uncertainty. Waves could come from the fault itself or from triggered landslides. A big quake could shear under the lake and lift or drop a slab of lakebed, sending a direct tsunami. It could also shake loose underwater slopes. Lake Tahoe has steep submerged walls, and past landslides into the lake are documented. In fact, an ancient large-scale slide at McKinney Bay, around 50,000 years ago, is thought to have caused a massive tsunami, possibly over 100 meters high, when it collapsed the dammed glacial moraine. That event is believed to have filled McKinney Bay with a colossal debris avalanche that marked the basin. The modern warning is that even a combination of quake-induced slope failure and fault displacement could amplify the tsunami. Simulations suggest the two effects adding up would be worse than either alone. Altogether, this means many of Tahoe's low-lying shorelines, marinas, beaches, homes could experience severe wave inundation if the West Tahoe fault breaks. What about the fault's history? The seismic and geomorphic evidence sketch out a pattern of intermittent large shocks. At Fallen Leaf Lake, Maloney's team identified at least 2 or 3 old events in the past 8,000 years. If the interpretation is correct, the Fallen Leaf segment ruptured around 4.1 to 4.5 thousand years ago, and perhaps again around 5.6 to 5.3 thousand years ago, the latter possibly triggering a drought signal in Nevada lakes. These events appear to punctuate otherwise long, calm periods. If the Lake Tahoe Basin's rough combined chronology is any guide, large quakes on the regional faults might recur on the order of a few thousand years. Researchers propose a recurrence of roughly 3 to 4,000 years for big ruptures on the Fallen Leaf fault strand, noting that 4,500 years since the last event already exceeds the average interval. On the other hand, some single-event evidence, for example a sediment layer dated about 7,800 years old, has led others to speculate that an even earlier full-length rupture spanned the whole West Tahoe Dollar Point fault about 7,800 years ago, but that is still under study. In any case, compared to California's frequent quakes, Tahoe's schedule is slow, dozens of small quakes every year, but large ones only perhaps once in many millennia. This is why the historical record is silent. Modern instruments cover only the last century or two, a blink in the fault's life. The United States Geological Survey summary is blunt. The West Tahoe fault shows evidence of Holocene earthquakes, but is relatively quiet in historic times. Even though the long intervals make big quakes seem unlikely on human timescales, the potential impact is great enough that planners and scientists pay attention. For instance, the Tahoe Regional Planning Agency and researchers have included West Tahoe fault scenarios in hazard maps and emergency plans. The United States Geological Survey even set up a scenario event, magnitude 7.1, under Tahoe, in its hazard systems, explicitly as a hypothetical for planning. It is crucial to emphasize that nobody is predicting an imminent quake. These magnitude figures come from modeling and paleoseismic data, not from a clock. They serve to illustrate a worst-case risk. As one seismologist put it, talking about bending and breaking a stick, you cannot know when it will break, but you know that if the strain accumulates sufficiently, at some point it will. What are the mechanics? If you could peer underground at the moment of rupture, you would see one side of the fault suddenly dropping a few meters relative to the other. Because the West Tahoe fault dips steeply eastward, an east block up, west block down motion is expected. That vertical displacement compresses water at depth and launches waves. The seismic waves themselves would radiate outward, causing violent shaking near the shore. After the main shaking, the lake might ring like a giant bell, sloshing back and forth for hours, the seiches. Modelling shows that these long waves have periods of minutes to tens of minutes, capable of sweeping beaches and shallows repeatedly. Meanwhile, underwater sediments that slipped or collapsed could cascade into deeper parts of the lake, causing local underwater landslides and turbidity currents as seen in cores. All told, the geology implies any big quake there would be dramatic, even if it goes unnoticed for now. For science enthusiasts watching Lake Tahoe, the takeaway is this. The West Tahoe Dollar Point fault is a real active fault zone, albeit one that only moves on very long timescales. It is real, and its threat should not be dismissed. We see its imprint in steep underwater cliffs, in offset lake floor layers, and in sedimentary slides dated thousands of years old. Although we have not felt its rumble in modern times, the physics of faults tells us that it can produce a magnitude 7 class earthquake if a long enough segment breaks. In the worst-case scenarios envisioned by researchers, a rupture could tilt the lake floor by several meters, generating tsunami and seiche waves up to about 10 meters high, about 33 feet. Communities on Tahoe's shores would need to contend with that, along with strong shaking. Scientists emphasize, however, that these studies are about preparedness, not prophecy. In the end, Lake Tahoe's tranquility today hides a dynamic tectonic story. The risk no one talks about is simply that time in geology is long. The last big quake on the West Tahoe fault might have been beyond the memory of written records. But the fault is there, and its mechanics follow the same laws as any earthquake fault. By combining geomorphic mapping, offshore surveys, trenching and seismic modelling, geologists have pieced together a sobering picture of what could happen. It is a powerful reminder that beneath even our prettiest landscapes lie forces that move continents and stir waters. Stay curious, Tahoe fans. The basement of the Jewel of the Sierra still has some chapters left to write.